In this video, we're going to be looking at section B, question 2 from the longer calculations questions. So really make sure you've had a go at this and really try to do the question. You've done all the calculation that you can before you look at the answers. Don't go straight to looking at how to do it. So it's a long question about sodium carbonate, which is a hydrated salt. So you're given the normal formula, which contains 10 water molecules per mole of sodium carbonate. That's going to be important to know. We're told it's heated, it's lost some water to crystallization, and the final answer we want is basically how much water it's lost. So what's the percentage loss of mass? We've got the initial mass of the solid. That's been put into a volume of 250 centimetres cubed in a volumetric flask. And then we titrated with 20 centimetre cubed, and we have the concentration of the hydrochloric acid, which is 0.1 moles per dm cubed. And then we're given a table of titration results. So obviously in a titration question, the first thing I'm going to do is think about this case because it's practical. I might do some little diagrams of the method that's going on. So if I move myself out of the way, you can see that I started with a solid. I've written the formula underneath, or at least the formula as we know it. We know that they then dissolved that in 250 centimetres cubed. I always need to remember that step that I take out a sample in a titration and put in a flask. So I'm not titrating the whole sample, only 20 centimetres cubed. And then I've got information about the burette, which contains HCl, and I'm going to put the information about the hydrochloric acid. Next to that, it's concentration. I don't know the volume yet. For the volume, I'm going to need to work with these values in the table. So the first thing I'm going to do is obviously work out how much acid was added, because all I've been given is the initial and final burette readings. So that's the next thing I'm going to do, is just simply take away the initial reading from the final reading to work out my 3 volumes of acid. Because it might be that I don't want to include all of those volumes in my actual calculations. This is the most likely place you may have lost a mark, is by assuming that we add all 3 and divide by 3. But actually, the 2 values on the right are the only ones that are close enough, so the error in a titration needs to be within 0.2 centimetres cubed. So my mean titer value is actually only going to be 20.65 plus 20.55 and divided by 2. I'm not using the rough. So that means I can work out moles of HCl. I've got the volume in centimetres cubed, so I'm going to divide by 1,000 to get decimetre cubed. And then I'm going to times it by the concentration of the acid. So far I've used all the information about the hydrochloric acid to get the number of moles in that titer value. So the acid is reacting with sodium carbonate. So I'm going to need a balanced equation for the reaction between sodium carbonate and hydrochloric acid. So write it all out first and think about the formulae of the salts. Hopefully we know the formula of sodium chloride is going to be kind of helpful. And that we make water and CO2 because it's a carbonate plus an acid. Looking at the balancing, I need 2 sodiums and I'm also going to need 2 HCl. So that's the most important thing, a ratio of 1 to 2 carbonate to acid. Actually, there's a quicker way you could have done this. So it turns out that all carbonate ions require 2 hydrogen ions to neutralize. This is the ionic equation for the reaction, and we'll look at ionic equations next week. So this is always what's happening when you react a carbonate with an acid. Hydroxides, it's a single OH minus, 1 H plus, so it's a 1-to-1 ratio of OH minus and H plus. But for carbonates, you're essentially taking CO2 out, leaving an O2 minus behind. So you always need 2 H pluses. So if you have something like HCl, you will always need 2 moles to react with a carbonate. So we have our ratio. I'll pop that in brackets and we'll probably come back to it when we look at ionic equations next week. Now I have a mole ratio. That means I can work out how many moles of sodium carbonate I have in that flask that I was titrating. So my moles of sodium carbonate is going to be my moles of acid divided by 2. Gives me 1.03 times 10 to the minus 3. And I'm going to write down not only that this is the moles of sodium carbonate, I've already written that, but it's in 20 centimetres cubed. Really important that we keep writing that down in these questions so that we realise what we've used. We're going to tick off what we've used. We've used the other volumes. I've not used 250 centimetres cubed. And that was the volume that my 20 centimetre cubes was taken out of, and that was the volume that my solid was put into. So my next step is how many moles there are in 250 centimetres cubed. So it's going to be the moles in 20 divided by 20. That gives me the moles per centimetre cubed. Times by 250 gives me the total number of moles in 250. Doesn't matter what order you do that in, you may have times it by 250 and divided by 20. Alternatively, you might have done 250 divided by 20 to get how many times it's diluted and then times by it. But that doesn't matter so long as you have worked out how much it's diluted by. This is quite an unusual question and it's quite unusual practical wise. So normally in a practical we would use a 100 centimetre cube volumetric flask and take out 10, or we'd use 250 and take out 25. So normally the dilution is a simple 10 times factor, or not a dilution, but 10 times sample. Sometimes they just write questions like this to make it a little bit harder. It's utterly fictional. There's not really any 20 centimetre cube pipettes. They're not very common. So it's very unlikely that we'd take out 20 centimetre cubed in real life. Important thing is I have the moles of sodium carbonate with or without the water, because the sodium carbonate reacts with the acid regardless of the water molecules. So what I have is the mass that went into the 250. I've got the formulae that I'm assuming, if that was the whole formulae, there were 10 waters. And I've got the moles of sodium carbonate that is genuinely in the flask. So I actually know how many moles of the Na2CO3 part that I have. So how would I work on from here to working out percentage loss of mass? Well, if I have moles and I have the formula, I can work out the MR of Na2CO3.10H2O. The sodium carbonate bit adds up to 106. And then I would just add the 10 waters separately. So I'd normally just do my 10 times 18 and add it on. So the total mass of that is 286. So the mass, the maximum mass of salt crystals, if they all contained 10 moles of water per sodium carbonate, would be the moles of sodium carbonate times by 286. That's going to tell me how much mass I could have had if I hadn't accidentally removed some of the water by heating. So this is the maximum mass. Jolly good, it's bigger than the initial mass. That's always something we want to check. If it's not, we've done something wrong because we're trying to calculate the mass lost. And so the mass lost in terms of a raw number is going to be the total maximum mass we could have had to take away what we've actually got left, which is 0.986 grams. So my percentage mass loss is therefore going to be the mass that I lost, 0.986, divided by the original mass, so the original maximum mass that it would have been, and that makes it 3.682. And then my percentage therefore ends up being 26.8%. So this question was slightly different. It's very common to have a percentage by mass, and in fact question 3 is a percentage by mass question. A percentage by mass, we would take an impure sample of a solid and then we'd be finding out how much of it is a particular chemical. So in the next example it's going to be an impure sample where some of it is calcium carbonate but not all of it, and then we're working out how much of it was calcium carbonate. This is slightly different because instead you're trying to work out how much mass is lost. Another example of this could be decomposition of a carbonate, for example. When you're heating it, you could work out basically the percentage that it decomposed by how much CO2 had been lost. But all we're doing is keeping our cool, calculating moles, using balanced equations, and making sure that we used every single number in the question. If we forgot any bits of it, there's still going to be transfer errors for doing each of the steps that I've talked through. Hopefully that was helpful. If you've still got any questions about this type of question, this type of calculation, or you want to know if you would have got a mark somewhere or anything like that, feel free to email me cksciencetuition@gmail.com and we'll talk about it in the Q&A at the end of the week.